Hello, maurieo. In this video, I'm going to take a look at calculating the equilibrant or equilibrant. Aha, you might say, what is an equilibrant? An equilibrant is a force equal to but opposite of the resultant sum of vector forces. That force which balances other forces, thus bringing an object into equilibrium. Aha! Well, I get that now. Well, perhaps when you see this diagram here, you'll get a bit of an idea of what we're trying to do. So determine the magnitude and position of the equilibrant of the following force system. Take moments about the left force. So here we're looking for, and I've put the answer in the magenta colour there, but we're looking for the single force that would balance that force system there, just as a seesaw, perfectly balanced and level. In this case here, you might have two small children and a little toddler on one side of the seesaw, and over here a sort of, if you can imagine, a larger person. I think the kilonewtons, we might be looking at considerably larger sort of weights, but you get the idea that it would balance or pivot about this point here and be perfectly level and in equilibrium, and this force here would then be called the equilibrant. So let's have a look at this system. What do we know? Well, we know two things. We know that the sum of the downward forces is equal to the sum of the upward forces. So very simply, we can add up our four forces, 15, 8, 20 and 42, to give a total of 85 kilonewtons. So we know that the upward force will be 85 kilonewtons. But where does it act? Well, we also know we have a second little equation up our sleeve, or a second truism, and that is that the sum of the clockwise forces, they're the forces that tend to move the beam clockwise, is equal to the sum of the anti-clockwise forces. In this case, that would be the single equilibrant. And we need to try and work out where that acts. So if we do a bit of investigation here, we can see that the sum of the clockwise forces is equal to 8. Well, first of all, we know that the 15 kilonewton force has no effect. It has no turning effect on the beam because we're taking our moments about the left hand end. So it has no effect at all. But we know that we have the 8 kilonewton force acting at 3 meters from the pivot point or the fulcrum, and then we have the 20 kilonewton force acting at 3 meters plus 4 meters, or 7 meters from the pivot point, and finally the 42 kilonewton force acting at 3 meters plus 4 meters plus 8 meters from the left hand side, the turning point or the fulcrum. So 8 times 3 is 24. 3 plus 4 is 7 times 20 is 140. These are kilonewton meters now. And 42 times 3 plus 4 plus 7 plus 8 is 15. 42 times 15 is 630 kilonewton meters, giving a total of 794 kilonewton meters, and this is the sum of the clockwise forces. Now we know that the sum of the clockwise forces is equal to 794 kilonewton meters, and that must be equal to the sum of the anti-clockwise forces, there being only one of magnitude 85 kilonewtons, acting at a distance, unknown distance, of x. So 85 kilonewtons times x must equal the 794. So therefore 85 times x is equal to 794. X divided by, or 794 divided by 85 kilonewtons must give us x. And we can see there that our, straight away, that our kilonewtons there would, our kilonewtons would cancel out. Just here, I'll just show that with a little line there and a little line there, cancel out, leaving the meters, and we could see that from there that of course that would be, and that works out at 9.341 meters. So now we know where our 85 kilonewton upward force acts. It acts 9.341 meters from the left hand side. And so once we get into magenta mode here, to put the little meters in there, there you are, we have our equilibrant.